We're going to be chatting about something called complex numbers. So notice this small little itty-bitty mistake. There should be an S up there. Complex numbers right there. And our goal, we're going to define, graph, and we're going to use complex numbers in solving today. So by way of introduction, we have two little problems right here. And see the top one, of course, and all we have to do is take the square root. And when we take the square root of both sides, remember to say plus or minus on this side. And so, of course, the question in our heads we ask, what number times itself will give me a positive 4? What number times itself will give me a positive 4? So one of the answers is 2. And then we realize that the other answer is negative 2, because negative 2 times negative 2 is positive 4. So what if we have a situation like this? Well, if we attempt to take the square root of both sides and we ask ourselves what number multiplied all by itself gives you a negative 4. And then we say, oh snap, it's not possible. So we've been saying no solution, or more specifically, no real solution. Historically, mathematicians would have simply said no solution. But then along came mathematicians that said, hey, let's play the what if game. And the what if game says, what if there was a number that when you multiplied by itself, you actually got a negative 4? So they played the what if game, and this is what they came up with. Is if you represent this as a number line right here, then these are all the numbers that you can ever think about, for the most part, can be plotted somewhere on this line. So take, for example, counting numbers. I can plot a 1, I can plot a 2. Rational numbers that include these numbers, but also decimals. So what if I said this? Oh, here's 1.5. I can plot that here. So that would be called a rational number, because I can write it as a fraction. But then we said, well, what about pi? Where would I put pi? And pi would be somewhere over here, 3.14, so approximately right there. But what about square roots? Take, for example, we already know that 2 is the square root of 4, but that's already been plotted. What if I said, well, where's the square root of 5 live? Well, the square root of 5 lives somewhere about here. So we can graph all of these. Look, I have the square root of positives. Look, this one here is the square root of 1 right there. This one's the square root of 0. Yay! So where do we put the square root of negatives? And therein lies the problem. So along comes some creative folks that said, well, let's just pretend that we can actually plot that. And they came up with a system here saying that, well, what if you did have square roots of negatives? Then above would be the square root of negative 1. And up here would be twice that, like so. Notice I'm not doubling the inside, I'm just saying twice on the outside. And this thing down here would be the negative of the square root of 1. And here would be twice that, etc. So they came up with this system. Now, what's funny about mathematics is they came up with this system and they called it imaginary because we're pretending. Well, it turned out that 200 years later, they finally found applications for this. It's not just imaginary. It actually turns up and shows up in real life situations. Two places that it shows up in real life. Not that we won't explore that much, but it does show up in electrical engineering. And instead of using I, engineering, they'll be using the letter J, which is the exact same thing. It also shows up in radar and in plotting in control towers when they're plotting and finding out where certain crafts are. Turns out that complex numbers help calculations go faster, so they are used there. So what we're going to do is do a basic introduction to complex numbers. We call them complex numbers because they look more complicated than we've seen before. Instead of being simply something on this number line right here, it turns out they come off the number line into a whole new world, a new fantastic square root. So let's define, what is an imaginary number? So we use the letter I for imaginary, and this is the definition. I is simply the square root of -1. That's it. So it's the pretend world. But it turns out pretend world helped us out quite a bit. Which therefore, if you were to square I, you would get -1. So these are two different ways of representing the same definition. I is either the square root of -1, or if you square I, you get -1. We write them in standard form, like this, where right here is like a 6 or a 7, something in the real number world. So this part is the real, and this part is the imaginary. Just like we talk about real numbers, we could talk about pure imaginary numbers, where we just say something like this. 3i, that's a pure imaginary number. Or I divided by 2, that's a pure imaginary number, because there's no real part to it. It's just taking imaginary and dividing it, or tripling it, whatever the case may be. We see lots of different patterns all over, and let's introduce it this way. If I were to take a -1 and I raise that to the power of 1, quickly we know what that is. It's just -1. But what happens when I square this? When I square -1, I get +1 now. So now let me continue that pattern and see what happens. Well, it turns out that if I were to cube it, I'm back to where I started. Look. I'm back where I started. And what if I were to quadruple it? Sorry, quartify it. It's a quartic. What do we end up with? Oh, a +1. So notice, look, the pattern goes. As the exponent increases, we just go -1, +1, -1, +1. So it cycles through only two things. So real quick, describe your neighbor. What's this going to be? We establish a pattern here. We know that this one has to be -1 for this reason. The odd numbers become -1, the odd exponents, and the even exponents become +1. Another way of thinking about that looks like this. What's the definition of even? It's divisible by 2. So let's take the 51 and divide it by 2. Why am I choosing 2? Because there are two numbers in the pattern. It's either a +1 or a -1. There's only two numbers in the pattern, so I divide by 2. Notice what I get. I get 25 with a remainder of 1. So look at this remainder. The remainder is 1, so it corresponds to this, to the power of 1. Because there are only two results in the pattern, we divide by 2, and whatever the remainder is, it puts us back up into here. It's either a 1 or a 2, and actually let's go back one. Technically it's 0 here, like so. But the pattern is true going that direction as well. All right, so we're going to do exactly this, but instead of dividing by 2, we're going to divide by 4, and we'll see why in just a second. Okay, I'm going to back up just a little bit. If you refresh yourselves from Algebra 1, do you guys remember what anything to the 0 power is? It ends up being 1. Anything to the 0 power is 1. Anything to the 1 power, which is what I is itself. So I'm just going to write down positive I there. Now, we know by definition, I squared is -1. So what is I cubed? I cubed is the same thing as saying I squared times I. So what is I squared? That's -1. And what is I? That's I So what do we get? This simplifies to negative I. Negative I. Which brings us all the way back to I to the fourth is just 1 again. So let's see the pattern. Just like with the negative 1, positive 1, that when you square or triple or cube, etc. This here, 1, I, negative 1, negative I, and back to 1 again. Which means this one here is going to repeat. Notice it's the same. So what is I to the 6th power? It's a negative 1. Why? Because it's the same over here. It's just the pattern being repeated. So what's I to the 3rd power? Excuse me, I to the 7th power? I to the 7th power is negative I, which is the same as I cubed. And now we're back down through our cycle, back starting again at 1. So what's the moral of the story? What if I had a number way out here? How did I get to equate, how did I equate the I7 to I3? What's the key thing I did? Well, let's refresh what we did over here. What did I do right there? I divided by 2. Why 2? Because there are, well, even, sure, and because there are how many options up here for results? There's only 2, a negative 1 or a positive 1. So I divided by 2 because there's only 2 options. How many options do I have here? 1, 2, 3, and 4. So the moral of the story is this. Take your exponent, divide by 4 because there are 4 possible choices, 4 possible results. What I get here is equal to 1 remainder 3. And this right here tells me that it's I to the 3rd power. The remainder tells you which of these it'll fit in. Remainder 0, remainder 1, remainder 2, remainder 3. So let me repeat. We take the exponent, divide it by 4 because there are 4 possible outcomes. The remainder just tells me where it is. So what's I to the 9 going to be equivalent to? Well, we take 9, divide it by 4, and we get 2, remainder 1, which means I to the 9th is I to the 1, which simply is I. There we go. Let me try another one. What about this? The opposite of I to the 12th power. The opposite of I to the 12th power. Well, 12 divided by 4 is 0. Excuse me, that's the remainder. Is 3 remainder 0. So now I can simplify the negative of I to the 0. So notice this negative in the front, I'm keeping in the front here. And what's I to the 0? We already solved that one, is 1. So the answer here is negative 1. It's a coincidence that it's negative 1. It's negative because of this negative in the front, the opposite in the front. So the next thing we're going to do is talk about how one would graph on the number line. And if you recall, and you guys all do, that standard coordinate plane looks like this. We call this X and we call this Y. And if I plotted a point right here, what you do is you look down here. Let's pretend I wanted to know what point this was. Well, I go down here and I see a 4 there, and I go over here and I see a 3. So what you say is this. The answer is 4, 3. We're going to do exactly this, but instead of using parentheses and a comma, we're going to write it as an imaginary number. Why? Because instead of talking about 2 dimensions, length and width, X and Y, instead of talking about space, we're talking concepts. Real numbers here, imaginary numbers here. So what we're going to do is try to figure out, well, what's the number, we call it the complex number, that this one represents. So if I were to pretend that this was an x-axis here, that would be a 2. And if I were to pretend that this is a y-axis, this would be my 3. But because it's on the imaginary axis, I'm going to put I next to it. So this is how I would write the answer. A is 2 plus 3i. The y, all you do is attach an I. Attach an I to the y. The x is just the x. So notice I'm not doing parentheses. I'm not saying 2 comma 3 with parentheses. I'm just rewriting it, but I'm using the same ideas. This is my x, this is my y, so this is my real, this is my imaginary. Your imaginary always needs to have an I at the end, like so. So let me do B and C, and then I'll let you work on the other 6. B here, this one here is -1, -2, -3, -4. So that would be -4. Now it goes up 1 on the I, so I say plus I. -4 plus I is what B is. B is a complex number, so anything living on this axis is just the real numbers. 1, 2, 6, -5, pi, square root of 2, all these things live there. This new stuff we've introduced is called imaginary, lives on this line, and then a combination of them live on the in the actual quadrants. And let's finish up C here real quick. C here corresponds to 1 and -3. So we say 1 minus 3i.